Welcome to Chapter 12, Section 7, called Spherical Geometry. This is for Integrated Math 2 or IM2. So I'm going to be reusing some of these videos from a previous video, so the problem numbers may not quite match up, although you will see a title at the bottom to let you know which number it's supposed to be. It's just a kind of a time saver there. Alright, so just to get started here on the front screen, the first thing you should see is your due date. I don't see that on my teacher preview, but you will see it on your student screen. The second thing is the number of attempts. We always have unlimited attempts on homework, tests, and quizzes. Number of questions just tells you how many are on this particular assignment. Grading policy is always best score, so whichever attempt is the best one is one you get to keep. And partial credit is enabled, so if you answer one of two questions correctly, you get credit for the one question, or however many you answered correctly. This also, if I understand correctly, goes into parts of a question too. If there's more than one answer within the question, there's partial on there too. Down here it says, please remember once you start your homework, you must finish it before you can work on anything else. And what that means is once I click start, down here in the bottom right corner, there's going to be a submit assignment button. This is how we finish an assignment. So what that means on the last screen is you can't work on anything because Alex is going to lock all of your other assignments and even the resources until you click the submit assignment button. What it's trying to do is leave this attempt open for you and not close it. If you say close this screen and you're not done yet, or you close your computer, it's trying to leave the attempt open for you. So just make sure that when you want to leave this screen, whether or not you finished, you click submit assignment so that Alex doesn't lock out all of your other assignments and resources. That's one huge reason to click that button. Another big one is that it actually affects the grade book when you click that button so that your teacher can see what you've been working on and hopefully it will improve your grade there. Alright, on the side we always have three resources. We have explanation. Explanation tells us that we're going to lose our current question attempt because it's going to give us the answer to this exact problem. So it's not going to give you the answers unless you come type them in. Example will give you something very similar to what it is we're looking at and kind of walk you through the idea here. Make sure you read through background information, especially if you see this section. If you don't see the background information, it's kind of introducing something brand new. That's the idea. So you can scroll through. Once you're happy with that example, you can close it. You can open another example so that you can see another one worked through if you need to. You can also message your teacher directly from the screen so we know where to come help you, because it attaches a picture of this problem on the email. So it's a good way to get specific help on a problem. All right, let's go ahead and get started. All right, so we're going to talk about a different type of geometry, and we definitely want to look at the example here because we need some background information. There's quite a bit of background information that we need to know in order to answer the questions that they're asking us here about Euclidean geometry or spherical geometry. So there's two different types, kind of depending on what we're looking at. So there's figures that are drawn on a plane, and that's described as Euclidean geometry, like this. Or there's spherical geometry, and that's figures that are drawn on a sphere. And they definitely interact a little differently than we're used to when they're on different pieces. So we're very much so used to Euclidean geometry. That's in fact what we've been practicing all semester. We don't practice spherical geometry as much, but what do we live on? We live on a sphere, right? So when we think of, like, say, the globe, we're not really using Euclidean geometry. We're using spherical geometry. We have to, because we have to look at things in a sphere. A lot of things in our universe are spheres, actually. So it makes a little more sense when we're talking about certain types of math. So we definitely want to have this background information. So in spherical geometry, a line is defined to be a great circle. So we can kind of see it's going around in a circle. Or we can see the blue or the red line. So they're kind of going around and they meet back to one end to the other. So a great circle is formed by the intersection of a sphere and a plane that contains the center of the sphere. The angle between lines in spherical geometry is the angle between the planes containing the corresponding great circles. So that one's a little bit harder to picture, and I know sometimes they do give us this more, which is a little nicer, so we can actually kind of see that they actually having to do with this 90-degree intersection, and we can see the great circle. They're showing it to us. We can see the two circles intersecting, and they're intersecting at a 90-degree angle here. So hopefully that helps you picture that a little bit better, because I know that's a little bit hard to read and just picture exactly what it's talking about here. The figure below shows examples from both Euclidean and spherical geometry. So we have line AB, line AC, and line BC are lines in Euclidean geometry. Also, line AC is perpendicular to line AB. So we can see we have three lines. They're all three intersecting in different ways, and we have a perpendicular, two lines intersecting perpendicular to each other. Then we have OS, PS, and OP. These are lines in spherical geometry, and like I said, they go all the way around the circle, and they basically connect back to each other, don't they? So they're not just a flat line that keeps going left and right, or whichever direction they're going. They're actually going in a circle. Also, line OS and PS are perpendicular to line OP. I almost said right, but this is a line OP. So we have OP going around this way, and this guy is perpendicular, as well as the red one is perpendicular. So we have OS and PS. So OS is kind of the red going around here, and then PS would be the blue one going around. So again, it's kind of this idea, they're perpendicular to each other, but what that means is that the intersection here is perpendicular to the other. All right, so now let's think about parallel lines really quick. So parallel lines, normally, Euclidean geometry, some lines are parallel. Kind of depends. Are they, do they have the same slope? Are they, at the same distance apart from each other? Will they ever intersect? In spherical geometry, there are no parallel lines. So they do not exist in spherical geometry. And we can kind of think, if you're thinking of like a globe and actually you kept drawing these lines, what we would have is longitude and latitude, right? Hopefully we've heard of those before if we're thinking about a globe. And they kind of seem a little bit parallel, but in the terms of parallel that we've learned, where they'd have to be the same distance apart and they never intersect, they'd all end up intersecting at the bottom and the top, or at the sides, if we kept doing these longitude and latitude lines. So there aren't any parallel lines for the great circles, because they all have to go through the center. That's actually kind of one of the requirements there, right? So the triangle angle sum theorem, that's one that we use all the time in Euclidean geometry, right? We have a triangle, and the sum of the three angles is 180 degrees. So I just did a plus sign for sum. So the three angles have to add up to 180 degrees. We know that. We've used it many, many times. But in spherical geometry, the sum of the angle measures of a triangle is greater than 180 degrees. So it's a little different because of the way that it's shaped in spherical geometry. Okay, so here I went and pulled a picture because I would really like to see that picture of the triangle. I think it's a little easier to help visualize. So I'm going to zoom in. Ooh, that's a little blurry because I kind of stole this one off the internet, but it's a little bit of a blurry sphere here, but you can hopefully kind of still make that out. And then they show us, here's our regular triangle, what we're used to looking at, where we have these nice straight lines on the triangle. Well, once we wrap it around a sphere, they kind of balloon out a little bit. Like I was saying, they make this kind of little balloon shape. So the angles aren't perfect. You see how it's a little bit bigger on the sides here? So they're not going to be perfect. They're going to be more than 180 because it's going to balloon out just a little bit. So that's just that idea. It's just that visualization there. And then down below here, it's talking more about the parallel lines. So it's talking about how we can always create a parallel line through a given point, not on the line. That's our parallel postulate. But in spherical geometry, we can't do that. You can never find a line parallel to another given line. through the given point. And that's as in, it's showing you example up here. So it's not going to be parallel to it, although it looks like it's kind of the same distance at certain points. They do end up coming closer and closer together at the top, and they end up intersecting. And even if you think about, longitude and latitude, there's usually the circle at the top. A lot of the time you see the picture of the circle at the top, but they're all coming to that point at the north and south poles, right? So they kind of all come together. All right, so we also know that in Euclidean geometry, the sum of the angle measures of a triangle is 180 degrees, and spherical geometry, the angle measures of a triangle are greater than 180 degrees, which, is why I grabbed this one. So they're kind of restating a few of the same pieces down here that they already stated up here. They're just kind of explaining them to us. All right, so let's go ahead and see if we can work through the statements that it gives us. So in spherical geometry, any two given lines must intersect. So we're just, looking at that on the example there, we can definitely see that those lines that I was kind of trying to picture as longitude and latitude would definitely come together, and we can kind of picture that on this guy here. So we have all of these lines, and they would intersect here at the top. So I'm going to go ahead and check that guy for true. In a spherical geometry, through any point not on a given line, there are no parallel lines given to that line. So yes, we read that a couple of times on that background page. In Euclidean geometry, that's the one we're used to, some quadrilaterals are parallelograms. And that's true. Not all quadrilaterals are parallelograms, but some are. In spherical geometry, the sum of the angle measures of a triangle is 180 degrees. So be careful. That's Euclidean geometry. That's our regular triangle here. That would be this purple guy here. But in spherical geometry, it's a little bit more because of this extra ballooning space when it kind of stretches out over the sphere. So this is not true. In both Euclidean and spherical geometry, if all three angles of a triangle have the same measure, they must all measure 60 degrees. Ooh, this is a test on that same idea. Because if all three are the same, and we know that it's 180 degrees, for Euclidean geometry, then I would divide by 3 and I would get 60. But if it's a little bit bigger, it's not going to be 180 anymore. It's greater than 180 degrees. Because of that circle, it's kind of pulling the triangle out a little bit, like that ballooning effect I keep saying. That's not going to be 60 degrees anymore for each one. It's going to be more than 60 degrees. Or none of these are true. So let's go ahead and see. How did we do? Yay! So with this one, some of the statements can be a little bit tricky. Just make sure you're paying attention to them. I would definitely try to keep your notes page open, because I have that background information on the notes page so that it makes it very easy. Instead of having to have it open and go back and forth, you can have your notes pages in front of you from class while you're trying to answer these questions. All right, so that was section 7. I will see you in section 8.